Swayam Prabha. Digital India. Educated India.
Welcome back, student, to this new week where we are still continuing the pipe flow. And last week we finished the lecture at finding the equivalent roughness of pipes and said that we are going to solve one particular problem. But I'll think it's better to take that problem after I complete this particular topic. So until this point in time, what are the things that we know? We need to find out an F. F is the Darcy-Webash friction factor, Darcy's friction factor, and that is F is equal to phi of function of Reynolds number and epsilon by d. So Reynolds number we can calculate if the flow is given, d is the pipe diameter. So epsilon we saw that we can find through these tables. Most of the cases, for your significance in practice for the numericals, you will be given the value of epsilon by d. So if you are able to calculate the value of epsilon by d and Reynolds number, then there is a dependence of these two parameters Re and d on the friction factor F, and if we know the friction factor, we can calculate by using these values and find out the head loss, the major head loss. Okay. So to do that, there is something called a Moody chart. So friction factor is a function of Reynolds number and relative roughness for round pipes is a chart like this, okay, where this is Reynolds number on x axis and F you can find out and epsilon by d is plotted on the right. So this is the oldest method of finding these friction factors, Darcy friction factor. However, for this course, of course, if you are given these Moody chart, you should be able to find a corresponding Reynolds number and a corresponding epsilon by d line here, and then go ahead and find out the respective F friction factor. But for your convenience, I am going to provide you two formulas. One is a Colebrook formula which relates this friction factor F to epsilon by d and Reynolds number. Can you see there is one trick in this formula? If you note, you will see F is also on the left hand side and F is also on the right hand side. That makes it implicit in nature. All right. But I still expect you to remember this formula. The solution for this formula can be done through trial and error. All right. Or you can use another formula which is totally explicit in nature, which is called Haaland equation. So here you see there is friction factor unknown is only on the left hand side. So if you know epsilon by d and you know Reynolds number, you will be able to find out the value of F. So this equation you must remember, and also this, because some of the questions could be based on Colebrook formula as well. All right. So with this thing in mind, so we can solve the problems now. Head loss was a function of friction factor, right? I mean, it was dependent on friction factor, and F was a function of Reynolds number and epsilon by d. So we can find F using these two formulas or Moody chart, and therefore we will be easily able to calculate the head loss. To demonstrate that, we have a question here that we are going to solve now. So the question says a badly corroded concrete pipe of diameter 1.5 meter has an equivalent sand roughness of epsilon s 15 millimeter. So we have already been given epsilon s. A 10 millimeter thick lining is proposed to reduce the roughness value to epsilon s of 0.2 millimeter. So a thick lining would be put which is 10 millimeters long, and this will bring down the roughness to 0.2 millimeter. The question is, for a discharge of 4 meters cube per second in the pipe, calculate the power saved per kilometer of the pipe. So, if you see, because of this epsilon there is going to be a head loss. So, head loss is related with energy loss. Energy losses, if you reduce that energy loss, you will save some power. So, that is the idea of this particular question. So, like always, we are going to start the solution on the white screen. Okay, solution number 7. So, we see before the lining, before the measure of reducing the head loss, before the lining was put, V1 is going to be Q by A, right. So, Q was 4 meters cube per second, area is pi by 4 into 1.5 whole square. So, this is going to be 2.264 meters per second. All right. For this particular case, Reynolds number is going to be, we call it RE1 as V1 D1 by nu. So, V1 we have already found 2.264. Diameter we know it was 1.5 meter and nu is 1 into 10 to the power minus 6. So, Reynolds number comes out to be 3.395 into 10 to the power 6. Similarly, epsilon S1 by D1, the value we have already been given in the question, is 15 into 10 to the power minus 3 meter divided by 1.5. So, it comes to 10 to the power minus 2. All right. So, if we empirical equation of Haaland, okay, then we can find under root 1 by F1 is equal to the things on the right hand side, and on calculating we can get, because this is an explicit formula, all right. So, F1 we can get 0.0379. Now, we have talked about the friction factor we have calculated before the lining was there. Similarly, let us talk after the lining was put. So, after the lining was put, diameter will be reduced. How much? 1.50 was the diameter and lining of this. So, the diameter becomes 1.48 meters. Therefore, the velocity will be 4 Q by A pi by 4 into 1.48 to the whole square. That means 2.325 meters per second. All right. Corresponding Reynolds number RE2 as we call it is V2 D2 by nu. So, 2.325 into 1.48 divided by 1 into 10 to the power minus 6. So, it comes out to be 3.44 into 10 to the power 6. Similarly, friction epsilon S2 by D, we said it has been reduced to 0.2. So, it has become 0.2 into 10 to the power minus 3 meter divided by 1.48. So, this value come out to be 1.35 into 10 to the power minus 4. All right. So, similarly, using the Haaland formula, you can calculate that F will come out to be 0.0132. Haaland formula. So, now we have calculated F1 and F2. F1 is a friction factor before the lining was put, and F2 is a friction factor after the lining was put. So, to continue further, all right. So, we are going to calculate head loss. HF is equal to FLV square by 2GD. Sorry. So, before the lining was put, HF1 would be 0.0379, that was the friction factor 1, length is 1000 and velocity was 2.264 whole square divided by 2 into 9.81 into 6.60. So, HF1 comes out to be 6.6 meter. Similarly, we will calculate HF2, same formula. F here, now the new F was 0.0132 into 1000 into 2.325, the velocity had changed, divided by 2 into 9.81 into 1.48, and this comes out to be 2.450 meter head loss. So, savings in head, you see the frictional loss before the lining was 6.6 meter and after the lining is put is 2.450. So, saving in head HS is HF1 minus HF2, and this will come out to be 6.6 minus 2.450. So, HS is 4.150 meter. Alright, this is saving in the head. Now, for power, savings in power would be nothing but gamma QHS, right? So, gamma is 9.79 into 4 into 4.15 kilowatt, because we have taken this 9.79 into 10 to the power, so 10 to the power 979 into G, so 9790, instead we did 9.7, therefore we written in kilowatt, and this will come to be 162.5 kilowatt. So, this is the saving in power. So, you see how we were able to find the major loss and the savings in major loss if we put the lining, which will reduce the friction factor in a pipe. This was a quite a illustrative example. All right. So, just writing it down, the final result here, that the power saving is 162.5 kilowatt. All right. Okay, moving ahead, there is another question that says air under standard condition flows through a 4 millimeter diameter drawn tubing with an average velocity of 50 meters per second. For such conditions, the flow would normally be turbulent. However, if the precautions are taken to eliminate disturbances to the flow, it may be possible to maintain laminar flow. So, the first part is determine the pressure drop in 0.1 meter section of the tube if the flow is laminar, and the second part is repeat the calculations if the flow is turbulent. All right. So, we will solve this question again on the white screen. So, solution number 8. So, under standard temperature and pressure conditions, rho is 1.23 kilogram per meter cube and mu is 1.79 into 10 to the power minus 5 Newton second per meter square, because we are talking about air. All right. Therefore, the Reynolds number will be rho Vd by nu. So, if you put 1.23 into 50, because velocity of 50 meters per second is given, diameter is 4 millimeters, so 004 meter divided by 1.79 into 10 to the power minus 5, and this will come to be almost 13,743, which would normally indicate turbulent flow. All right. However, since we have been told assume this is a laminar flow, we say if the flow were laminar, so friction factor will be given by 64 by Re. Therefore, in this particular case, although it is turbulent, but we say assume that it is laminar, so we will find the friction factor, which will come almost to 0.00467. Therefore, drop in 0.1 meter long horizontal section of the pipe would be delta P is equal to F into L by D, our formula, into V square rho V square by 2. All right. So, delta P is going to be F is 0.00467, length is 0.01, diameter we already know 0.004 into half into rho is 1.23 and V square is 50, and this is going to be 179 Newton per meter square. All right. So, we can calculate everything here. So, 179 Newton per meter square. All right. So, we could have actually used directly the formula for delta P, but now before we go to the next part, it says if the flow were turbulent, then F is a function of Reynolds number to epsilon by D. So, if we look at the I told you, if we know what type of pipe it is, we can look down the epsilon value. So, of course, it is I have not given it here written in the question, but if you look at the table, from table epsilon will come to be 0.0015 millimeter, okay, because it is a drawn tubing. All right. So, epsilon is 0.0015 for drawn tubing. Okay. So, we calculate epsilon by D, which is 0.0015 by diameter is 4 millimeters. So, we get 0.00375. all right, and Reynolds number came out to be earlier 1.37 into 10 to the power 4. All right. So if use either Moody chart or Haaland equation corresponding to Reynolds number is equal to 1.37 into 10 to the power 4 and epsilon by d of 0.00375, we will get F as 0.028. All right. Therefore, the pressure drop will be F into L by D into half rho V square, and after putting 0.028 into length will still be the same, diameter will still be the same, rho is 1.223 into 50 square. So delta P is going to be 0.076 kilopascal. So the pressure drop, as you see, is much more when the flow is turbulent. All right. In the first case, it was only 0.179 kilopascal. All right. So we talk about the minor losses now. We have talked much about the major losses, but now we must put our focus a little bit on the minor losses. So minor losses is due to the change of the velocity of the flowing fluid either in the magnitude or in the direction. Okay, if the magnitude or the direction, any of them would change or both will change, the losses associated with them is called minor loss in pipes. So this is a typical flow pattern through a valve that is shown here. It will comprise of both major and minor losses. See, the minor losses occur due to if there are valves present, if there are tees, if there are bends in the pipes, if there are reducers, and there are other appurtenances. All right. So minor losses also have a common form of this. So it is KL multiplied by V square by 2G. Okay. And this KL is the minor loss coefficient. In terms of Q, we can also write Q square by 2GA square. So this is minor compared to friction losses in long pipes, but can be dominant cause of head loss in shorter pipes. So if the pipe is long, because the major loss is given by F into L by D, you remember, 2V square by 2G. All right. So if the pipe is long, the major losses would be too much, but minor losses in long, this is called minor because the frictional losses come, due to these phenomenon of like bending, contraction and expansion are less in case of long pipes. Therefore it is called minor losses, but it's not always minor. If the pipes are of shorter length, the term minor losses actually will be dominant. Now let us see the loss due to contraction. A sudden contraction in a pipe usually causes a marked drop in pressure in the pipe due to both increase in the velocity and loss of energy due to turbulence. That is a well established fact, correct. So you see there is a fluid that is coming with velocity V, and after the contraction, sudden contraction, the velocity changes to V2. So in this case, for a contraction, the head loss, the minor head loss will be Kc, that we don't know yet, into V2 square by 2G, not V1. So, if the V2 you should be able to find using the continuity equation, and Kc either you can derive it, or but most of the cases in many general scenarios it is given. Okay. So, if this is the contraction depicted by point 2, so fluid at point 1 goes a contraction and is at point 2, we write head loss is KL into V2 square by 2G. And what is this KL? KL can be found out as a function of A2 by A1, what the area 2 and area 1 is, okay, ratio of the areas. So, A2 by A1. So, most of the time you would be given these values directly, or a curve like this will appear, but for certain standard conditions you are expected to know this. So, in case of sudden contraction, okay, you see, you can assume safely KL as 0.5. This means A2 was 0. Okay, so basically A2 is not 0, but A1 is so large, this area is very large, like reservoir compared to this area. In that case, you see, according to the curve, this comes at around 0.5. So, sudden contraction, when it means, it will always be implied that you have to assume KL is equal to 0.5. Please remember this. In case of a sudden contraction, KL is 0.5 and V2 square by 2G when multiplied with this will give the minor losses. So, head losses due to pipe contraction may be greatly introduced. So, you see, due to sudden contraction there is going to be head losses. Now, our aim as an engineer is to reduce those head losses, correct, and that can be done by introducing a gradual pipe transition called as confusers. So, confusers are used to introduce a gradual pipe transition, something like this. You see, there is an angle alpha. In that case also, the head loss is going to be Kc dash another coefficient K into V2 square by 2G in case of contraction. But what that Kc is given by this this graph. So, this is Kc on this side. For every alpha, we go and look at what this A2 by A1 ratio of A2 by A1 is, and we pick a point, for example, and try to find out what that Kc is. In such cases, either you will be given this graph or you will be exactly told what the Kc is. All right. Now, in this particular case, head loss due to gradual contraction, you see, we had one equation, and we can also write this in form of another thing where both V2 and V1 could be used. So, KL into V2 square minus V1 square by 2G, okay, in case of contraction like this. You see, this is 2 alpha and this is alpha, and here also we are going to use, for different alpha we have different KLs. In that case, you do not have to worry about area of 1 and area of 2, because it will already be taken care by the velocity continuity equation, A1 V1 is equal to A2 V2, just a different way of writing. So, this will simply give you, suppose if you have 15 degree, you can assume, like if there is a 15 degree alpha is there, then you just take the linear interpolation as 0.24 will be the KL. So, one advantage here is we do not have to worry about the ratio of A2 by A1. This looking at the table is pretty simple. I do not expect you to remember this, but you can be given this type of table in your assignments and exams, and could be asked to find out the value of KL and corresponding the head losses. So, in that cases it will be V2 square minus V1 square by 2G. All right. So, a different set of data, there is a, see, many people have done lot of experiments, and different set of data for gives this for different angle, gives ratio of, I mean the value of k as a ratio as a function of a2 by a1. So, for example, first you calculate a2 by a1, if it comes 0.50 and look at the angle, let us say it was between 50 to 60 degrees. So, this k can be assumed as 0.06, all right, and head loss can be calculated as k into V2 square by 2. So, whole thing has already been given here. Now, I think I should finish this lecture here with the gradual contraction. When we meet in the next lecture, we will talk about enlargement. When there is a pipe enlargement, what is going to be the minor loss. So, this is all for this lecture, and I will see you next. Thank you so much.